Number 5. Given the reaction represented by the following unbalanced equation, okay, I'm actually telling you here that it's unbalanced, but when in doubt, assume it's unbalanced and balance it, right? If it already is balanced, awesome, all the better, okay? But always assume it's unbalanced so that you make sure it is balanced. But I'm telling you here that it's unbalanced. A, write out the balanced chemical equation. So I actually have the formulas, so that's nice. So I'll just copy those down nice and neatly. We're including the states of phase because they're given to us. That's a good rule of thumb. If you're not sure, you should include the states of phase in any given time. If the question or the prompt gives you the states of phase, you include the states of phase. Okay. Now, let's keep track of nitrogens first. Why? Because it's the first element I come to as I read left to right. 2 nitrogens on this left side, 1 on this right side. And so what I can do is I can put a coefficient of 2 here in front of NO2. That would balance my nitrogens. I'd have 2 on each side. So let's count the number of oxygens. We'd have 3 on the left side, 4 on the right side. That's no good automatically. Now, one of the things that I've found personally that can really help, if I get in this situation where my coefficient might be 1, 1, and 2, like my initial trial here, but I find that the number of oxygens is odd on one side, right, because of this bad boy right here, it actually helps to double all the coefficients straight off the bat, right? So it was 1 and a 2. That had my nitrogens balanced. I'm going to double those to 2 and 4, okay, 2 and 4. So now let's count where we're at. 2 here, 2 nitrogens, that'd be 4 nitrogens overall. 4 in front of this, that would make 4 nitrogens overall, so the nitrogens are balanced. But now let's check how many oxygens we have. If we had a 2 for a coefficient here, that would make us 2 oxygens, plus 2 more oxygens, 4 oxygens. A 4 is a coefficient over on the product side, that would actually make 8 oxygens. Well, that's not balanced. But notice what I have left to do. I have an even number of oxygens on this reaction side and O2 by itself. So I can actually manipulate this coefficient however I want, and it'll only affect the number of oxygens. So 8 oxygens, 4 oxygens. I can simply pump this coefficient up to a 3 to make 6 oxygens here, 2 here, for a total of 8 on the reaction side. And so the balanced chemical equation is going to have a coefficient set of 2, 3, and 4. B reads, what is the mole ratio of NO2 to O2? Now this might seem like a very simple question, and it is, but I want you to remember that being able to do this simple task has its foundation in you being able to balance a chemical equation. If you cannot do chapter 8 stuff, you're not going to be able to do the simple chapter 9 stuff. So the mole ratio of NO2 to O2, that would be 4 to 3. If 20 moles of NO2 form, right, so that's the product, how many moles of O2 have been consumed? So let's make sure we show our work with a little bit of room that I've shown here. Here is our given, and here is our unknown. Now we're still in section 1, so we're, for the most part, going to be dealing with mole-to-mole conversions. We're going to work into mass-to-mass conversions, but for now, mostly, we're going to stick with mole-to-mole. And so we are moles of NO2, and I'll convert out of moles of NO2 into moles of O2. Moles of NO2 will cancel. Moles of O2 are the only unit that I have remaining. Now all that's left to do is plug in the numbers. So what was my ratio of NO2 to O2? Oh yeah, it was 4 to 3. Some simple math. 20 times 3 is 60, divided by 4, that'd be 15. I'm considering 3 significant figures right there, so my final answer is 15.0 moles of O2, if you want to get all the way complete there in your response. D. Twice as many moles of NO2, okay, that's your product, form as moles of N2O are consumed. Is this true or false? Well, I can look at these coefficients, and I can see that the coefficient for the product, NO2, is in fact twice as much as N2O. Now, if you're thinking to yourself, well, that doesn't take into account the mass, the different molar masses of these two different substances, and they do have slightly different molar masses. In this situation, however, the mass of these substances does not matter, because we are counting how many moles are being generated or consumed. And so we are just going to concern ourselves with the coefficients. So I'm going to go with true. And lastly, E, twice as many grams of NO2 form as grams of N2O are consumed. Well, that kind of piggybacks on what we were just talking about. Yes, in terms of the number of moles, yeah, we're getting twice as many moles of product as the reactant are consumed. However, like we already pointed out, these two substances have different molar masses. And so the ratio of grams, the ratio of mass going on here is not necessarily the same. And so here I am going to go with false.